Welcome to the Introduction to Computer Science and Computer Programming subject. In this video we are going to show you about the basic elements. We're going to make the introduction to the subject and the general aspects of computer science and computer programming. I hope that you will enjoy this video. Of course, the first thing that you have to define is what is computer science and what is related computer science about the problems, algorithms, and programs that computer science rely on. Computer science can be defined several ways. You can see here what is the Wikipedia page that tells you the definition of computer science, and maybe the best thing is reading what you have in the square in the right that says that computer science deals with the theoretical foundations of information and computation together with practical techniques for the implementation and application of these foundations. We can see here two different parts. What is the theoretical part that tells you about computational models that are followed by computers in order to solve the corresponding problems, and the practical part that is related to the two sides in computers, the hardware part that is computer architecture and structure, and the software part that is computer programming and software development. So the question is that we use computers to solve problems, but what kind of problems? Not all problems can be solved by a computer. For example, you have a simple problem, just like adding 2 plus 2. You can give this problem to a computer, and this computer can give you a solution to you. This problem is solvable. But sometimes there are problems that cannot be solved. For example, if you ask a computer how can you win in this football match you are playing, whatever is the other team or whatever is your team, your features, the computer won't be able to answer to this question, can't solve this problem. So this defines the types of problems that a computer can solve. Computers solve only what are called computational problems. Computational problems, of course, are also quite large, a reduced set of all the possible problems that you can find in your life. More specifically, we can say that most computational problems are numerical analysis problems, that is, they're related to mathematical problems, or word and natural language processing problems, that is, those related to processing the different words, the different tests, the different forms of the language that you can give to a computer, or can be graphical representations that are very useful in order for representing on the screen different objects of the material world or your imagination, whatever they are. In any case, computational problems can be solved by using what is a sequence of commands, and a sequence of commands defines what is called an algorithm. An algorithm is something that you use in a computer in order to solve problems. The computer needs, by one side, what is the input information, that is the data that you are using for solving the problem, the features of the problem, the specific values that you need for solving the problem. And the computer will produce an output information that is the result of the solution of the problem. But for getting these results, what you will need is an algorithm or program that is reflected in the computer that indicates to you how to transform what is the input data into the output results, that is the final information, the final solution of the problem that you are going to solve. Therefore, the different features that you have to define in order to obtain an algorithm are the following. First one is the algorithm must be finite, that is, it has to stop in a natural way. When you start processing your input data, you will have in a finite time what are the output results. Second, must be definite, that is, has to have a clear effect. Each pass, each step that you take in your algorithm must have always the same result given the same input data. Of course, an algorithm must have an input and an output, that is, data and results. An algorithm must be effective, that is, must be reproducible by human users. That is, you can follow the algorithm in order to obtain the same result for always the same input data. And finally, the algorithm must be general, that is, must work for any kind of data that is sensible for solving the problem. And although algorithm seems something that can be really special, really related to computer science, they are not really related to computer science because humans employ algorithms in order to solve problems. In fact, you have been learning algorithms during all your life. For example, when you face the problem of how do you make this sum, that is 2314 plus 378, how do you solve this? When you were a child, what you had to do was the following steps. First, you wrote one number below the other, all of them aligned to the right. Then you selected the two rightmost digits that represented the units of the two numbers. And you make the addition, the sum of these two selected digits. Then you have to write the result below the column where these two digits are. In this case, the result is 12. 4 plus 8 is 12. Since you find that the sum is greater than 9, you have to take only the units of this partial sum, and the tenths have to be carried for the next column. Then you go to the next column on the left. In this case, you have to add all the digits plus the possible carriages, and you have to write the result below the column where they are. In this case, the result is lower equal than 9, therefore you don't have any carriage. Then you go to the next column to the left, you select these two digits, and you add them, including the possible carriage. In this case, you have no carriage. You write the result below the column they are, and you make the next column to the left, and you add the corresponding digits that you have. Since in this case you don't have digit in the number below, you consider this as 0. With this, you have the result for this column as well. When you are going to move to the next left column, what you find is that you don't have numbers anymore. Therefore, the final number that you have written is the corresponding result. You have followed an algorithm in order to solve this problem. Of course, you can apply algorithms to other activities. For example, how to open a door with a key. In this case, what you have to make is hold the correct key in your hand, put it into the keyhole, and then you have to turn in the proper direction as many times as you need. And then you will have to open the door. Of course, some problems can be solved by different algorithms. For example, if you face the problem of having to determine if a positive integer number n is prime, you can have many possibilities. All of them will be characterized by a similar process. The process will be checking if any number between 2 and n-1 is a divisor of the number n that you are checking is prime or not. If none of these is a divisor of n, then n is prime. So different algorithms can solve this problem. For example, in this case, you can define a first algorithm that says you that the steps are: consider all the different numbers I between 2 and n-1, and for each number check if the number divides n. If any of the numbers divides n, then stop saying that n is not prime, and if none of the numbers divides n, give us a result that n is prime. A more detailed definition, a more detailed algorithm could be this one. Follow these steps. First, let I to be an integer number with value equal to 2. If I is equal to n, then you say that n is prime. if I divides n, then you stop saying that it is not prime. And in any other case, what you make is change the value of I for one more unit, and then you go to step 2 until step 2 or 3 accomplishes the condition and the algorithm stops, saying that n is prime or not. A third algorithm can be defined based on these two properties of prime numbers, that are that when n is greater than 2, that is even, that is a multiple of 2, is not prime, and that all divisors of a natural number are lower or equal to the square root of this number. So based on that, what we can make is define the third algorithm following these steps. First one, if n is equal to 2, then n is prime, and you stop the process. Second step, if n is multiple of 2, that is finishes in 0, 2, 4, 6, or 8, then n is not prime, and you stop the process. In any other case, what you have to do is making a equal to 3, and if a is greater than the positive square root of n, then you say that n is prime and you can stop. Otherwise, you check if I is a divisor of n, say in that case that n is not prime, and you stop the process. And in any other case, what you make is adding to the value I 2 more units, that is, you only employ odd numbers in order to check that n is prime or not, and you go to step 4 one more time. This algorithm is better than the two previous algorithms, and you have to think about why this algorithm is better than the two previous. And the main reason is that you don't have to perform as many operations as the other two algorithms in order to determine if the number is prime or not. In general, you employ less time with this algorithm with respect to the other two algorithms. That is what makes this algorithm better than the two previous. And of course, you can represent this algorithm not only by natural language, you can represent in different formats. And in fact, humans can accept in different formats. For example, you can see here what is a graphical description of what is the corresponding algorithm for determining if a number is prime or not. And you can see here the natural language description that we have seen a few minutes ago. But the problem is that computers cannot accept algorithms in the different formats. In fact, if you give, for example, the graphical description of the algorithm for n is prime to a computer, the computer will get puzzled. It's impossible for the computer to process this type of algorithms. Computers can only process algorithms that are represented in what is called a programming language. That is, algorithms that are represented by programs. If you give a program to a computer, the computer will take the program, will make a process, and will give you a result. In this case, the number is prime or not. So computers can only accept algorithms written in programming languages. That is, they only accept programs, and programs get executed in a computer. That is, the different steps that are defined in the program get realized and get executed in the computer in order to find the final result. When the program is executed in a computer, it gets transformed into process. A process is a dynamic program. That is, a program that gets an evolution, because it starts with an initial state with a set of data, for example, the value of n, the initial value of the auxiliary variable I, in order to determine is prime or not, and you perform what is called a computation step, an instruction of the program, in order to transfer this data into another data that constitutes a new state. On this data, on this state, you can perform another computational step that will transform in a new state, and this will be performed until the end of the algorithm, until the end of the program. With all of this, we can see that we need the definition of what is a programming language in order to write what are the algorithms into a computer. And we are going to see the different programming languages and models that computer science has defined all along its history. Programming languages appear from an evolution of the primitive calculation machines. In fact, the first calculation machine that was developed was Blaise Pascal's Pascaline, that was used for making additions. Pascal's father was a tax employer that used to make many additions, and Pascal built this Pascaline, this machine, in order to ease the task of his father. In this case, only additions can be performed by this machine. A few years after that, Gottfried Leibniz built a multiplying machine that was able to perform products, but only products, only one type of operations. All these were mechanical engines, and mechanical engines were used as well for Charles Babbage in order to create what is the analytical engine. That the main novelty with respect to the two previous is that was the first programmable device. That is, it was not limited for only one operation. It can perform many different operations, additions, multiplications, subtractions, and so on. Anyway, it was a mechanical device, and it didn't work at the moment that he built it. And a few years ago, some scientists tried to reproduce it with more technology, and they found that it was correct. That is, that worked properly for the different programs that you can roll. In fact, this was the first programmable device and employed what was employed as well for modern computers. That was the punch cards that were used for the textile industry in order to write the different programs. Was his wife, Charles Babbage's wife, Ada Lovelace, the first person that wrote computer programs by using these punched cards. Many years after Charles Babbage developed the analytical engine, Alan Turing, a very brilliant mathematical English mathematician, defined what was a Turing machine. Turing machine is not a real computer, it's a theoretical model that defines what a computer can do with very, very simple instructions. And this is the paradigm, the theoretical model that is followed by modern computers. And Alan Turing used this paradigm in order to create what was one of the first computers, the Colossus project, that was developed in Great Britain during the Second World War in order to make code-breaking operations on the Nazis' communications. But finally, what was the first digital computer, modern digital computer, was the ENIAC computer that was built in the United States by John von Neumann team. John von Neumann defined what was the architecture for the ENIAC computer, and with all his team developed this computer that was the first one to be digital and fully programmable, and was a complete milestone in the story of computer science, of course. As you can see, when you are working with computers, you need to store data and program in the computer, and the computer will execute the program on this data for generating results. Therefore, you need to store data and program, and you employ what is called the memory in the computer to store this data and program. If you use the same memory to store data and program, of course in different parts of the memory, you are using what is the von Neumann, the so-called von Neumann's architecture, that stores in the same memory program and data. There are other architectures that make a separation of program and data in different memories, but this is the most popular one, the von Neumann's architecture that stores program and data in the same memory. Another computer has to execute this program. For this, you need a processor, a CPU, a central processing unit, that will execute the program on the data stored on memory as well. You will need a control unit inside the CPU in order to execute the program. That is, the control unit will take the instructions that you have in the program in order to make the execution of the different instructions that you have in this program, the different steps of the algorithm the program is representing. And you will need an arithmetic and logic unit, ALU, in order to retrieve data and make the operations that the control unit is taking from the program. That is, the control unit will take the different instructions from the program and will use the arithmetic and logical unit in order to retrieve data, make the operations, and of course returning what are the results into the memory. As you can see, programs and data are stored in the digital memory. And in digital memory, what you have is a binary representation of data. That is a memory is a sequence of binary code in sequence positions that are called addresses, where you store both instructions and data. Therefore, when you are going to make an instruction, for example, multiply the value of two numbers and store in another position of the memory, what you need are, by one side, what is the data, and by the other side, what is the instructions, and they are stored in the digital memory. That is, they are sequences of binary code. For example, if A, B, and C are stored respectively in addresses 24, 33, and 3T in hexadecimal, they have the binary representation that you can see. And you need, in this case, as well, the codification of the instructions of the different operations that you can make. For example, loading the data, multiplying the numbers, and store the result. Therefore, you will have an encoding for this operation that can be, for example, the one that you are saying here in this right part of the screen. Therefore, when you write the program that performs this operation, in order to store all this in the digital memory, you have to make something like that. The first line is saying load what is the value that you have in A, that is in the memory address that you have the A value. Second, make the multiplication of the value that you have retrieved by the value that is stored in the address of B. And third one, getting the result stored in the position of memory of C. Of course, this is really difficult to understand. This is what is called the matching code, that is native code, the binary code that is used by the computer, and it's very difficult to be understood by human users, by human programmers that are finally what the people that are going to write on the programs. Therefore, our first attempt in order to alleviate this situation was defining mnemotechnics in order to say what are the binary codes corresponding to each mnemotechnic. For example, load will be the 10111100, and 24 with the corresponding binary representation is indicating that you are loading what the data that you have in position 24. After that, you have the multiplication of what you have loaded by that you have stored in position 33. And finally, you store this result in position 33. This is what is called assembler languages. And they employ this kind of mnemotechnics in order to make easier the task for programmers. Anyway, those two are called low-level languages because they are very close to the computer hardware, that is, to the binary code. And of course, they are not a comfortable solution for programmers. Therefore, with the evolution of programming languages, the first large step that was done was defining what was high-level languages. High-level languages have as many advantages that they are closer to human language, that is, the representation of a program in a high-level language is more similar to what is a natural language representation. They are safer with best error checking, that it is is easier to debug the possible errors that you make when you create the program in this kind of languages. They are portable, that is, you can execute in different computers by only using the corresponding translation into the binary code for that computer. and they are more legible. They are more they are easier to read and to maintain and to modify with respect to what are low-level language programs. However, they have some drawbacks. The first one is that you need to translate high-level languages into binary because computer only understands binary code, and that they are slower than a direct implementation in binary code or even in assembler. However, since they give many advantages with respect to what is employed assembly or binary code, high-level languages have a high level of success, and in fact, all computer scientists what use mainly are high-level languages. We are going to see the evolution of high-level languages and the principal milestones during the evolution of high-level languages. The first high-level language that was developed was Fortran in 1954. It was developed by mathematicians in order to implement formulas. In fact, Fortran is from formula translator. That is employed basically for solving mathematical problems. After Fortran, many other languages, high-level languages, were developed. Lisp, Algol, COBOL, APL, Simula, and many others. However, at the late 60s of the 20th century, happened what was called the software crisis. The problem was that programs written with these high-level programming languages were very difficult to maintain. That is very difficult to correct the different errors and to update the corresponding features of the programs. The solution that was given for that was the use of structured programming, a new paradigm in programming which was taken by Pascal, a very popular programming language in the 70s, that give more clarity more clarity to programs and an easier way of maintaining the programs, because avoided some practices that were very usual in previous programming languages that made really difficult to maintain the programs. After Pascal, many other languages appeared in the structured programming feature. For example, C, that is a structured programming language as well, and SQL, that is not a proper programming language but is used for databases in order to query databases. However, one more step was taken in order to make programming activities easier, and of course in order to reduce the elements of programs that you have written once, in order to reuse for different large programming projects and very large projects. And this was the object-oriented programming. Object-oriented programming appeared with Smalltalk in the late 70s, but really exploded with C++ and Ada in the early 80s of the 20th century, and of course was really impulsed by the development of the Java programming language and its link to the network and internet in 1991. What are the features of structured programming? Structured programming was the paradigm that was developed in order to solve the program crisis. Basically, structured programming is based in that you employ program blocks that have single input-output points. That is, you cannot jump from inside these blocks into inside of other blocks. What are the different types of blocks that you can use in structured programming? The sequence block, that is, one instruction follows the previous one. The decision block, that is, you take a decision and follow one branch of instructions or another branch of instructions. And finally, the repetition, that is, according to a condition, you repeat a block of instructions. With the three different blocks, it was mathematically demonstrated that any algorithm can be implemented in a computer program. That is, you can solve any possible problem that you have with these three different blocks, these three different types of instructions. What is about object-oriented programming? Object-oriented programming employs internally structured programming, but it's a different paradigm because you create what are called sets of objects in order to create your application, your program, And these objects have some features and have the possibility of communicating among them in order to solve the final problem. For example, imagine that you have to develop an application for controlling a ventilation engine. You can have a subject, a sensor for the concentration of CO2, for example, a controller that tells you if the engine has to stop, go faster, go slower, and so on, and of course the engine itself that makes the ventilation. So the sensor, for example, can send what is the CO2 concentration data to the controller, and the controller will take the decision of fixing what is the engine speed to the engine. The engine can send the current speed to the controller in order the controller can send a new speed or keep the same that you have at this moment. By using this evolution with the different objects, the different entities that you have in your program, you are solving now the problem, for example, in this case of controlling what is the corresponding engine for ventilation. This can be applied for many other situations, and in fact, object-oriented programming is the most dominating programming paradigm that you have now in the software industry. Anyway, what happens is that although you write high-level language programs in structured programming and structured programming object-oriented, not object-oriented, you have, in order to make the computer to execute these programs, to translate them into binary, because computers only understand binary code. Therefore, the way of changing, that is, of translating these high-level languages into binary code is of main importance. And there are two main different tools in order to make this translation: compilers and interpreters. You have the high-level language, and of course you have to translate into the machine code. The translation process has too many different alternatives: compilation and interpretation. What are the features of each of them? Compiler acts in the following way. You have the high-level language code, which is called the source code. This source code is passed to the compiler, and the compiler generates a machine language, a binary code that is called the object code. This is stored in the memory and can be then executed by the computer. As you can see, the translation is complete from the source code, the high-level language, to the object code, the binary code. However, when you use an interpreter, you have source code. An interpreter takes the first instruction in the source code and translates into the object code, the machine language, the binary, and then it gets executed. After that, it takes the second instruction in the source code, translates it, and gets it executed. Make the same with the third one, and all the other, until you write to the last one in the source code, where you have the final translation into object code and the corresponding execution. That is, in this case, is a line-by-line translation and execution of the source code, not a complete translation. Therefore, the difference between a compiler and interpreter are related to perform a complete translation or a step-by-step translation, to make execution after translation or simultaneous execution. This makes that compiled programs are faster than interpreted programs. That is, make a faster execution in a compiler than in an interpreter. And one more advantage that is provided by the compiler is that syntax is checked before the execution. Whereas in the interpreter you have a simultaneous syntax checks with the execution. Therefore, most programming languages use compiler option, although many others as well use interpreter option. For example, compiled languages are C, are Pascal, are Java in a special way, and interpreted languages are languages like Python, or even Java can be seen as an interpreted language as well. We are going to see the feature of the Java language because this is the language you are going to use during this course. and you are going to learn the many features. What are the features of Java language? Java is an object-oriented language, and since it's an object-oriented programming language, the programs are defined as a set of classes. A class is what is the generic representation of an object. That is, you can say that a car has a series of components and features, and a specific car has the values of this component of these features. Therefore, the class what makes is the generic definition of all the objects that can be of this class. An object is a specification of this class. Java is platform independent because it can be executed in different operating systems and different hardware, provided that you have what is called the Java virtual machine we are going to see in a few moments. And this Java virtual machine is the core of the execution for the Java language. This makes very special what is the development of the Java language, because the source code is composed by the source code for several classes, as many of different objects that you are going to use in the corresponding definition of your whole program, your whole application. All the source codes must be compiled by the Java compiler, and the Java compiler will create the byte codes for each class. This is not really the object code, it's a kind of object code, but it's not binary. It's an intermediate language that then is taken by the Java virtual machine along with the Java libraries that gets in charge of translating these byte codes into the binary code that the operating system sends to the hardware in order to get the program executed. So you can see that in this case what you have in the compilation is a transformation into an intermediate language, what are the byte codes. And these byte codes get executed by a Java virtual machine that is a layer that is on the operating system, that is as well a layer on the hardware that has the final execution for the program. This makes that the process for programming in Java is that you have to write your program, that is your source code, in a text editor. When you save this Java statement into a file, you get the source code that gets read by the Java compiler. The Java compiler creates what is the byte code, that is the .class files that get stored in the disk as well. These files are read by the Java virtual machine that interprets the different byte codes and sends the corresponding execution of the program, that is the corresponding binary instructions, to the computer to obtain what is the program execution. So you can see that in fact Java is a mixture between what is a compilation in the first process and what is interpretation on the Java virtual machine process. Finally, you can understand that programming is not only about writing programs. Programming is an activity that gets run with a lot of tools and a lot of environment activities that contaminates you about or eases you activity of programming. Therefore, I'm going to see as a final matter for this video what are the elements of the programming environment and the different programming activities that are related to that. In a programming environment, you can find, for example, debuggers. What is debugging? Debugging is correcting the errors that you have in your program. It's very difficult to write a program without errors, and sometimes it's very difficult to correct them. Debuggers allow you to correct easily all these possible errors that you have. Some examples of debuggers are the BlueG debugger that you can see in this figure, or the Eclipse environment debugger that you can see in this other figure. You have as well documentation generators. All programs that you create, all programs that are created by professional programmers, have documentation because they indicate how to use and how to modify the code that you have developed, the programs that you develop. Therefore, it's very, very important to generate the documentation that is useful for using the programs or modifying the programs. There are documentation generator tools that makes make easier this task and allow you to develop this documentation that can be used by many other programs or by yourself in order to modify your own programs. Operating systems are the environments where programs get executed. Operating systems are the access to the functions of the hardware by abstracting what are the difficulties of the hardware. For example, if you have to write a character on the screen, this depends on the monitor that you have, the screen that you have, the graphic card that you're using, and the different hardware that you are using in this moment. Operating systems allows to avoid this difficulty of specifying for a specific hardware by making a unified way of accessing all the different hardware that you have available. Operating systems are very popular, as for example Windows, Linux, or the Apple operating systems that are very popular for you. Apart from when you are rating programs, you have to rate these as plain test programs. But sometimes you will need as well some advices, some aid in order to make easier what is the task, this tasking of writing the program. Some editors and integrated development environments, IDEs, allows you to make this easier. For example, in this case you have here what is the Eclipse environment that gives you the different classes that you have in your project, the different variables that you have available, the different errors that you have found during this process of compilation errors. Or this, for example, that is Beans, that is a very popular one as well, where you can find more interesting features than in the other one. Or the Visual Studio from Microsoft that is used usually for the development application of Microsoft programs. Apart from that, for interacting with the computer, you need sometimes a graphical user interface and desktops that give you an appearance, common appearances to this the interface with your computer. There are as well command line interfaces, but graphical user interfaces are easier for most users and got very popular in the latest years. You can see, for example, in this case, what is the GNOME graphical user interface, or the KDE, or the Unity user interface. This allows you to manage the computer by using a graphical interface that makes easier accessing many of the features that you have in the computer. Databases are tools that allow you to store data in an organized way that makes easier the access to this data and makes more secure what is the maintenance of this data, avoiding possible losses of information or replication of information with the possible inconsistencies that you can have when information is replied. Databases are store all this data, and this data must be managed by what is called a database management system. These are some of the different providers that you have for database management systems that allow you to create, to access, to modify, and to get security operations on databases that allow you not to lose possible data or to get only access to given users and so on. Of course, nowadays internet is very popular, and many people has computers and has many other devices in order to access what are internet, and specifically what are web services and browsers. Of course, you will program in the future some applications for what is the different web applications. You will have the client part, you will have the server part, and you will have many browsers in order to access the different parts, and you can develop plugins for these browsers in order to give functionalities to the different web services that you have available. In the last 5-7 years, mobile devices have become a really popular tool for most people, and programming for mobile devices, of course, is getting a very popular market. Mobile devices are devices like tablets, like smartphones, and of course you have many different operating systems, and you can develop applications for these different mobile devices like Android, iOS, or Windows Mobile. Finally, in the last years, cloud computing has become very popular. Cloud computing consists of you don't have all your data or your applications in your computer, but they are distributed in many servers and in many different computers that can be given by different users around the world. This is what is now the cloud. And you have here all the applications, platform infrastructures, and data that you need in order to make your activities for programming. Of course, the infrastructure that you need is really big, and sometimes only some providers can give you this capacity, and these are some of the providers that provide cloud computing service nowadays. Finally, in the future, it's supposed that everything will be connected, and you will have to make the algorithms in order to make the different programs in order to manage this connectivity that is called as ubiquitous computer and intelligence of internet or Internet of Things. This is related to that you will have chips in everywhere, in every place, in everything that you have. You will have in your clothes, you will have in your phone, you will have in the streets, you will have in the traffic lights, you will have in your fridge, in many other places, and they will be connected in order to make more efficient use of the resources that you have. For example, only to turn the lights on when it's necessary, that is when it's dark and when some people are passing under that area. Or, for example, giving the supermarket an order in order to give to you to your fridge different food that is not available to you at this moment. Therefore, you will have an interconnection with all the things that you have at home, on the streets, and this will give to you public services in the future. And of course, this will be a very important layer of market when you develop in the future program applications. With this, we finish this video. I hope you enjoy it, and thank you for watching it.